Okay.
All right.
Well, let me also introduce you. So welcome everyone back for our next seminar. Today we are very happy to have Ben Webster from Braverman Institute and the University of Waterloo, who is going to tell us about non-commutative resolutions of Coulomb branches. Please take it away.
All right. Thank you. Right. So that's the title. And here's the depiction of my life. I don't know. I saw this image on the front of a book a very long time ago, and somehow it really stuck with me. And then I started living it. So what I'm gonna do in this talk is try to explain what I've been thinking about and trying to figure out with 3D n=4 theories over the past few years, and hopefully will be more like the top level image rather than the bottom one. Not be totally confused by trying to look at a different field. So the sort of first starting point, and please, I don't know everybody's background in the audience, so please yell at me if I'm sort of assuming background that people have or not assuming the background that people, wait, sorry, I think I got that wrong. But anyway, if I'm assuming inappropriate background, either too much or too little. But I started here by saying, what I've been thinking about with 3D n=4 theories. And for a while, that was just like a set of symbols that I sort of knew related to some stuff that interested me, but now I understand a little better what that means. So, the reason I had encountered that idea at all is I sort of started out interested in symplectic singularities, and kind of interesting symplectic algebraic varieties. The most famous example of such a thing being the nil cone. There's sort of lots of other interesting symplectic algebraic varieties whose singularities are somehow encoding something interesting about representation theory. And then eventually I learned that all of the examples I cared about, maybe not all the examples, we'll see, I don't know, but all the examples that I care about come from 3D n=4 gauge theories. Probably should have said field theories, because there's some that aren't gauge theories. And the way they come is that every 3D n=4 supersymmetric field theory gives me two natural spaces. It's Higgs branch and it's Coulomb branch. And those spaces, in cases that interest me, turn out to be lots of different, very interesting varieties. In this talk, I'm mostly going to talk about the Coulomb branch, but that's a little bit of a kind of artificial thing because there should be some duality on theory. So everything that's a Coulomb branch should be a Higgs branch and vice versa. But sometimes it's easy to write down the theory that something is the Coulomb branch of, and very hard to write down the theory that it's the Higgs branch of, or vice versa. And at least in the sort of gauge theory context we understand, you learn very different things about a variety by seeing it as a Coulomb branch compared to seeing it as a Higgs branch. All right, so what are these spaces? Well, as I say, the sort of case we understand are gauge theories. And for me as a mathematician, basically all other cases are some sort of motivation that I don't understand yet, but maybe hope to at some point in the future. The Higgs branch is a hyper-Hamiltonian reduction. So Tn is a complex representation, so it already has a Kahler structure coming from the fact that it's a complex vector space. When I take its cotangent bundle, I get a hyper-Kahler structure, and I can do a hyper-Hamiltonian quotient. And the Coulomb branch is defined in a very different way. It's chiral ring, which is, from the perspective of thinking of it as an algebraic variety, it's the functions on it as an algebraic variety, is the homology of an interesting moduli space. It's the moduli space of principal G bundles with a section in the associated bundle for the representation n, so that's where n comes in, on a space that's called the raviolo. So that's two formal disks that are glued to each other away from the origin. And just to have a name for this space, I'll call it the BFN space. And I can write that as a fiber product. So if I look at the moduli space of principal bundles on a punctured disk, then that's my section gives me an element of Taylor series valued in this representation n. And then I have to look at gauge equivalence. Doing that requires choosing a trivialization of the principal bundle. So I have to mod out by Taylor series in G. If I do that on a punctured disk, I just replace everything with Laurent series. So I look at Laurent series in N, modulo Laurent series in G. And I can think of this raviolo as a fiber product. I look at two copies of the moduli on the disks and requiring my principal bundles to glue into a principal bundle on the raviolo is saying, well, I map down to the principal bundles on a punctured disk, and I take the fiber product. So the homology of that space has a multiplication that comes from some natural stuff in geometric representation theory. And so that gives me a ring, which is the chiral ring of the Coulomb branch. I know that was a very fast summary of something that can be its own talk for a whole hour. So that's just to kind of give you a little bit of a flavor of what kind of ingredients go into this Coulomb branch. These are both singular affine varieties. They have a C star action and have a Poisson structure of degree -2, which in sort of physics comes from a secondary product. And that's actually, oh, no, that's not what I want to do. Sorry. It's just trying to turn on do not disturb. I'm having some trouble. I don't want my computer making dinging noises. Sorry, got distracted there. So the degree -2 part, this all comes from the fact that its D dimension equals 3. So this is one of these things that probably to physicists is totally obvious. When I learned it, it like blew my mind, right? That being in 4D, being in 3D, you know, we have a cohomological field theory, which in general is not topological, but then we put a topological twist on it. And when we do that, well, sort of point operators at different points, there's some multiplication for each pair of points. They're all homotopic to each other, but there's an additional operation that comes from looking at a two-sphere around the origin and sort of integrating over all the different ways those points could come together. And that gives you the Poisson structure, which to me, that was like a mind-blowing thing. All right, are there any questions? So this is sort of table setting. You can kind of accept this stuff as black boxes, but on the other hand, I don't want to just kind of blow past this if people have any questions.
Is this setting, I'm sorry, I'm turning off my video because I'm continuing by phone because I have no Wi-Fi here. Thanks to the storm.
So these spaces, one thing we can do that's pretty common is we can smooth them out by varying parameters of the field theory. So there are things called Fi parameters. Those are valued in the dual of the center of the Lie algebra. And moving those around, well, that means when I take this hyper-Hamiltonian quotient, I have to choose 3 moment map levels. So I can vary my moment map levels, and I will get different varieties. In particular, like moving 2 of these, so a C's worth of parameters, C tensor to this guy, changes the complex structure, and will actually often turn this guy into a smooth affine variety. And the third one does, from the perspective of algebraic geometry, a resolution of singularities and varies the Kahler parameter of that resolution of singularities. And for the Coulomb branch, sorry, that's on the Higgs branch side. For the Coulomb branch, you can do a similar thing, but now with mass parameters, which are valued in the Lie algebra of the torus of the flavor group. So I have this G acting by N, and I look at all the things in GLN that normalize it. I mod out by G, and that gives me this flavor group. And you have to work a little bit more to see how these vary things in the Coulomb branch, the way I like to think about it is you can make your gauge group bigger. You can get the gauge group that's the torus in the flavor group times G. And that actually has a symplectic action of the Langland's dual torus to the torus in the flavor group. And you can do Hamiltonian reduction with respect to that guy. And if you want to do the resolution, you take a GIT quotient. So this is the construction in Braverman-Finkelberg-Nakajima's paper, line bundles on Coulomb branches. All right. Are there any questions? All right, so a slightly more physical thing where one try, these Higgs branch, the Coulomb branch, they're really telling you about one very specific part of your field theory. So they're telling you about two different topological twists of the field theory, which people usually call the A twist and the B twist. And when you do these twists, then the rings of local operators will be the chiral rings of the Coulomb branch and the Higgs branch, respectively. So really sort of lots of questions, constructions, etc., involving the Coulomb branch or involving the Higgs branch, you can really think of as constructions in these topological twists of the theory, the A side or the B side.
Sorry, hi Ben. Can we go back one slide? I have a question about these parameters. So is that true? The Fi parameter just controls the Higgs branch and doesn't touch the Coulomb branch, and the mass parameter just changes the Coulomb? Or?
I hope I have not reversed these. I think I carefully checked and I got this right. I've gotten them backwards in the past.
Okay.
What happens is when you vary the Fi parameters, or at least what physicists tell me, is essentially you kind of destroy the Coulomb branch. The Coulomb branch becomes a bunch of disconnected points. What ends up happening is these parameter spaces correspond to tori that act on the opposite guy. So the flavor torus acts on the Higgs branch, and there's an action of the Langland's dual of the center of G that acts on the Coulomb branch.
You mean the dual flavor group? Dual flavor torus act on the Higgs branch, or the?
No, there's if you just have this gauge theory, right? The normalizer of G acts on N, right?
Yeah.
And so it acts on T star of N, and that action descends to the quotient. So the flavor group acts on the Higgs branch. And so when you deform the mass parameters, you end up with the fixed points of the corresponding C star in that flavor torus on the Higgs branch. And similarly, that dual of the Lie algebra of the center, that's the Lie algebra of the Langland's dual of the center of G. And so again, if you vary the Fi parameters, the Higgs branch will kind of smooth out, and you'll get the fixed points of that torus action in the Coulomb branch.
Okay, that's a good one. Thanks.
Yeah, that looks good. Yeah.
So yeah, I mean, I'm not intending to really try to talk about duality much in this picture, but this is sort of how you explain one of the kind of interesting predictions of duality, that the Higgs branch and the Coulomb branch should have actions by two different tori, which in nice cases, the fixed points are in bijection, which is basically like if you go to sort of generic generic mass and Fi parameters, you just end up with the torus fixed points on sort of both sides, and they get identified with each other. All right, cool. Okay, so somehow this was a very interesting thing for me to learn, that these Higgs and Coulomb branches sort of are really connected to topological field theories, topological twists of this 3D theory. And so you can sort of try to study other aspects of those field theories. And the one that I am closest to understanding something about, and one that's kind of relevant to the story I want to tell, is the category of line operators in these twists. And actually, especially this construction of the Coulomb branch, you can really think of it as it's a computation of take the trivial line operator and the trivial line operator and look at junctions between those. And that would be the same as local operators, but really somehow this fiber product description, that's something about joining together two trivial line operators. That this n mod g, this is something about like, you know, you're looking at the trivial line operator. So you have fields that are valued in n, and you're looking at what happens to, as I get close to a line, and I don't force them to have zeros and don't allow them to have poles. Whereas this ng, this is something about like what happens when you remove the line. And so you allow yourself to have an interesting junction. All right. So these categories of line operators actually have a really beautiful description. And I should have written this here. At least my sort of understanding of this is mainly due to Justin Hilburn and Phil saying you. And unfortunately, I'm not sure they've ever written a paper about this. But this stuff is kind of floating. I think it's discussed maybe in Justin's paper with Tudor and Nick Garner and Mike Garaci. Right. So you have these categories of line operators, and you can kind of think of them as monoidal categories. That's not quite true. They're actually factorization categories, but you should think about like, you should be able to take two lines and then kind of merge the two lines together. So they're factorization in the sense of like, oh, there's actually some OPE as the lines are close to each other. And it's not just they bang into each other, but you can kind of visualize it that way. It helps. So the category of lines in the A twist is the category of D modules on the loop space of n mod g. So this is again, you know, something about like, I'm looking at a disk, I'm pulling out this point and thinking about what happens as I sort of extend that infinitely in one direction. And somehow some magic of how the twist behaves means you're just getting D modules on this loop space. So you can think of that, this is helpful for sort of comparing with the other side as the coherent sheaves on a de Rham stack or de Rham space. And if you don't know about de Rham spaces, don't worry too much. I just like this because it gives you a very sort of symmetric presentation for what's going on. Because in the B twist, what you're getting is some version of coherent sheaves. There's a bit of throat clearing about exactly what kind on a de Rham version of the loop space. So the only thing that's different is the taking the de Rham, which means like, it's a strange thing to do, but it's basically you force everything to have a flat connection. And there's a way of sort of saying that in a consistent way in the world of stacks, that there's sort of a canonical identification between infinitesimally close points. And you're just doing that in somewhere slightly different. So I think this description is so beautiful, it's worth saying, even if you don't necessarily know very much about what de Rham stacks are. And so you can interpret this BFN description of the line operators, of the Coulomb branch, as actually a computation in this category of D modules on the loop space. You go and read Ginsburg and Chris and say, oh, how do I calculate the self X of the push forward of the line operator that says, don't allow any poles or require any zeros. And it tells you, oh yeah, it should be the homology of this fiber product. All right. And more generally, we can construct a kind of line operator in the A-twist called vortex lines, where we fix a subspace in this guy. Remember, this is the Taylor series in N, and mod out by some subgroup of the gauge group. And then we can push forward from the quotient of U by the subgroup to this guy. So in particular, the trivial line is that I take the Taylor series in N and mod out by the Taylor series in G, and then I look at the push forward to this quotient, this loop space. So I sort of think about all the ways of extending over a disk, and then I push forward by the map that's forgetting what happens on the origin. And in the B-twist, we have another set of line operators, the famous ones, which are the Wilson lines. So there's a line operator corresponding to every representation of G. And the way you should think about this, right, when I have this hyper-Hamiltonian quotient, well, for any representation of G, I can define a vector bundle over that guy by doing the associated bundle construction. And that's sort of a manifestation of the Wilson lines. Are there any questions?
Yeah, so just to make sure, can we go back one slide about the A-twist and B-twist? So you call the A-twist the Coulomb branch, or not quite?
So the A-twist, again, I hope I have this right. I don't think I have it backwards. The B-twist corresponds to the Higgs branch. The A-twist corresponds to the Coulomb branch.
So it's like you have some theory and you do some twist, A-twist or B-twist, and the Coulomb branch are like the homomorphism of some special object in that
yes.
Guy. And okay, so okay.
Yeah, I mean, it's so I like to think of quantum field theories as some kind of generalization of an algebra, right? It's you have some points and you have some multiplications of things at different points. And so one of the things you can look at is essentially the center of the algebra, the thing that kind of acts on everything in the picture. And that's this ring of local operators. And what you do when you take this twist is either you're adding in a differential, or if you like listen to Kevin and Owen Gwilliam, they actually sort of already had a differential, and what you're doing is deforming it. And so, these rings are basically taking the cohomology of two different differentials acting on your field theory.
Mm-hmm. Mm-hmm. Okay, thanks.
And they have some common degeneration, which isn't topological anymore. It's, sort of an interesting next frontier in this whole story. It's understanding the guy that's holomorphic along the C direction. Any other questions? So somehow, to me, the important idea here is, we have all these stories about stuff happening for the Higgs branch or stuff happening for the Coulomb branch, and all of those are really exploring some small piece of bigger category, this category of line bundles. And basically what my talk about is how you can learn some interesting stuff by looking at a little bit more of that category, looking at a bigger piece of it. So one way that this can happen is actually via some kind of abstract nonsense. If I have an invertible object, an invertible line operator, and again, remember, for my purposes, line operators, they're basically a monoidal category. So I mean that there's some other object you can tensor it with and get the identity line. Then that gives you a partial resolution of the Higgs branch. Oh, sorry, I should have put these in the other order. Of the Coulomb branch, if it's a type A, if it's an A in the A twist, and the Higgs branch, if it's in the B twist. And basically you do this in such a way that on your resulting partial resolution, You get an object corresponding to that line operator, and it's an ample line bundle. Basically, you construct this guy exactly so that it will be an ample line bundle. And it's, basically you take the powers of this line and look at some hom, and that tells you the projective coordinate ring. And this is actually sort of another interpretation of a construction that we talked about previously. So we get an invertible vortex line. Yes, what's up?
We're going down to a store, so if you come downstairs, that probably means we're still there.
Okay, but I'm busy right now, so have fun at the store.
That's for the warning.
All right. Anyways, pardon the interruption. So invertible vortex lines correspond to co-characters into this flavor torus. So we said before that we could get a resolution by varying our mass parameters. And that's actually just another way of saying that we take the vortex line corresponding to a co-character, and we do this general construction of making a partial resolution with it. And similarly, invertible Wilson lines give us characters of G, and you can use those to construct resolutions of the Higgs branch via doing GIT. So both of these guys can be phrased in terms of GIT quotients, but it's somehow actually secretly some more general construction involving invertible lines. And if you just sort of follow through, if I write down the projective coordinate ring of something, then coherent sheaves on proj of that are modules over the projective coordinate ring, modulo those that are zero at some large enough point. So when you follow this through, what you find is on this partial resolution, the derived category of coherent sheaves, well, every line operator gives me a coherent sheaf, but some of them will give me zero. So coherent sheaves are quotient category, and which ones give me zero? Which ones do I have to mod out by? They're the ones that have this X group zero for all sufficiently large K. So it's basically when you take the sum of these X groups, you get some module over the projective coordinate ring. And you want that to eventually be zero once K gets big enough. And one thing that will be very important for us is this sort of categorical quotient construction has a kind of automatic splitting.
Ben, did Tudor, can you say again, what's the physics interpretation of this? Did Tudor and the guys give this? I thought their statement was simple. It's just the category of line operators is the category of coherent sheaves. But you're saying that's not quite true, that you have to take this quotient?
Yeah, you have to take this quotient because there will be line operators that just give you a trivial coherent sheaf.
What's wrong with getting a trivial coherent sheaf? Why can't we allow a lot of zero objects?
Well, but then it's not the same category. Right? So, one way to think about this is, do a simple like B-side example. Like let me just skip ahead a little bit, right? If you have n equals Cn and G equals C star, then your Higgs branch is, or the resolved Higgs branch is T star Cp n minus 1, and the affine guy is the minimal nilpotent orbit. And all the Wilson lines go to non-zero coherent sheaves, but there are going to be like cones of maps between Wilson lines that are going to go to zero, where the map between coherent sheaves will be an isomorphism, but it's like not an isomorphism over the unstable locus that you pull out. So right, like I mean, I would say in this case, like the category of line operators is, I mean, again, maybe that's not the whole category of line operators, but at least one important piece of it is you take the zero locus of the moment map and you look at C equivariant coherent sheaves on there, right? And there are going to be examples of those which are supported on the unstable locus. And you can throw them out. I will need to think about an actual example, but you should get one basically by thinking about like what happens if you take a polynomial ring and you take the one-dimensional module over it and do a free resolution of that and then turn that into coherent sheaves. That's essentially the thing that will be sort of bad, there's a non-trivial line operator that corresponds to that guy, but there's not a non-zero coherent sheaf on T star CPN. All right, in particular, right, there are different resolutions. You don't see this very clearly in the T star CPN case, but there are other cases where you have like genuinely different resolutions. And those can be sort of written as quotients of line operators in different ways. Which, on the Higgs branch side, that's basically, you choose a different character to do your GIT reduction. There's a different unstable locus, so there are different sheaves you have to kill. So are there any other questions?
So maybe one question. Are there objects that are not visible by any of these invertible lines?
I think so. I would need to think about it a little bit, but yeah, I mean, I think so. I mean, there are a lot of different D modules on that loop space. And so like, certainly, if you're only looking at the vortex lines, I think there will be ones that like just like don't have any non-trivial X with any vortex line.
Okay. Okay.
Right. I haven't thought extremely carefully about this.
Okay. Thanks.
Mm-hmm.
So, but Ben, again, you're quotienting just by things that are supported on the unstable locus. Is that correct?
So in the type, in the B twist, I think that's a good way to think about it. I mean, this category of line operators, I mean, it's bigger than the category of equivariant coherent sheaves on the zero level of the moment map, right? Like, I mean, exactly what this B twist a line operator category is actually pretty subtle. Like if you look, Braverman and Finkelberg wrote these notes for a summer school in 2018, where they talk about this, that you have to use this notion of like singular support for coherent sheaves. Like it's a pretty complicated category. So I think like for the purposes I want to talk about, the important point is, yes, that you're pulling out this unstable locus and you're killing stuff that's supported on there. I think there might even be kind of more stuff in the category that you can't see with any of these resolutions.
So then this is nice. This is sort of just the way you describe, just if you were dimension down, just trying to describe coherent sheaves by thinking of the Higgs branch of the gauge theory, this is the kind of thing you end up with anyhow, right? So I think that's nice. It's natural. Okay, good. Thank you.
Yeah, of course. And I think it is useful to think about, like, if you have an affine variety and you're taking a GIT quotient of it, like what's the relationship between coherent sheaves on the GIT quotient and equivariant sheaves on the guy you were quotienting out? You have to kill some stuff. And it's exactly, this like stuff that's perp to high powers of the
Okay, that's
character that's going to turn into your ample line. Okay. So, and the thing I was going to say is, sort of canonically, there's a subcategory you can construct basically by taking the adjoint of this quotient functor. And I will probably screw up whether I mean the left or the right adjoint. I guess in this case, probably the left. And the way you can think about this is if you have a coherent sheaf on this partial resolution, you can write it as a complex of line bundles that are big negative powers of the ample line bundle. And then you can construct a line operator where you replace those with big negative powers of the object L. And that's going to be a copy of the coherent sheaves on this partial resolution sitting inside the category of line operators. And this is, I should say, this is all happening in like DG categories. I said derived category, but I really mean everything is a DG enhancement. All right, so I have this copy of coherent sheaves on the resolution inside my category of line operators. And well, given any other set of line operators, I can ask, when I mod out by the perp to those guys, which is really the same as take the X algebra of the sum of these guys and take DG modules over that. So essentially what I'm doing is I'm looking at, okay, given these line operators, how much of the line operator category do I see? I just throw out anything that doesn't have any interesting X with those guys. And well, this copy of coherent sheaves on the resolution either maps to this guy by an equivalence or it doesn't. If it does, then we call this set a window. And one reason this is a useful notion is if you happen to find something that's a window for two different invertible lines, then you can get a derived equivalence between the two categories of coherent sheaves, which can be very non-trivial. All right, well, that's an interesting notion, but do any such things exist? So this is mainly an idea that's been studied in the B-twist, where I think it's gotten a fair amount of attention. So this is this example I was talking about before of, C star, several copies of C where it acts with weight 1. We get CPn minus 1 as a resolution. Note in kind of two different ways, depending on whether the Wilson line corresponds to a positive integer or a negative integer. If you're thinking about this in the GIT world, right, like you're looking at C plus a dual copy, Cn plus a dual copy of Cn. You're looking at the zero level of the moment map, which is when the two vectors are perpendicular. And then depending on the character you choose, either Cn will be the unstable locus or Cn dual will be the unstable locus. So there's sort of two different ways to pull out a locus and get T star CPN. And the question is, does Cn go to the CPN or does the dual copy go to the CPN? All right. So it's a well-known theorem. I maybe shouldn't credit Bailenson with this because he did this for CPN itself, not T star of CPN, but the proof is basically the same. That if I take n consecutive integers, take the corresponding Wilson lines, that will give me a window. And these get sent to line bundles on T star CPN. And I'll note here, it depends on the sign of L, which line bundles they go to, whether they go to OK up to OK plus n minus 1 or to these guys.
So Ben, at this point, we're just working with the category of coherent sheaves. Okay, a particular description of it that comes from GIT quotients, right? Your description of Coulomb branches in terms of modules for some quantized, like your description of line operators on Coulomb branches in terms of modules for some quantized Coulomb branch algebra, is it useful here at all, or we're just talking about B-type brains on the coherent sheaves?
At the moment, I'm talking about the B-twist. I'm trying to convince you that this notion, that any examples of this notion exist.
Are you going to get something else in the A-twist?
Yes, we'll talk about the A twist.
All right, great.
So in the B twist, various people have worked on this. I think the sort of person who did the most interesting work is Dan Halpern-Leisner, who sort of essentially gave a description of windows for each invertible Wilson line. He sort of described a very large collection of these windows in type B. The construction is a little implicit. He sort of doesn't give you like, consider this object. It's like, consider the coherent sheaves satisfying these properties. But this is mostly just like, okay, this is a notion which exists. And now I'm going to try to tell you how to construct these on the A side.
Right. So sorry. So in the Halpern-Leisner's construction, he didn't give some generators, right? He just gives some.
No, he just gives the subcategory.
Right.
I mean, I think there's this other paper of him and Stephen Sam where I think they actually do.
Right, the magic window that they do. That's line boundaries.
In a number of cases. But yeah, so I just, in part, I just want to make the point that this is not like a totally weird, surprising notion. It has come up quite a bit in the type B case, in the B twist case. So something that happens a lot for me is in the B twist case, you're dealing with very familiar objects. You're doing some GIT quotient, symplectic reduction. Everything seems very familiar. And the A twist case sounds very strange. And it's very, like at least for me 10 years ago, it was very like, what is this thing? How do you define any of the objects here? So, what I hope to kind of convince you is that the A twist is not actually a lot worse than the B twist. It could be even better depending on your perspective. So, I say that in part because you'll have to bear with me for a couple of slides while I actually try to describe this construction. So, we're on the A side. We're thinking about this loop space and mod G. So let me just remind you, this is Laurent series in N, mod Laurent series in T. And on here, well, we have an action of the flavor torus, and then we have the loop rotation C star action. Let me just say this guy's loop rotation. So it comes from actually rotating the ravioli. And inside there's a subgroup, which is the nth roots of unity. So the unique finite subgroup of order n inside C star is a group. And I'm going to make a choice here. I'm going to choose a homomorphism from C star to this flavor plus loop rotation group, which acts with weight 1 along the loop rotation. So really, I'm just choosing a co-character into the flavor torus. And what I'm going to want to do is let this order n subgroup act on n via composition with this homomorphism. So this is a weird thing to do. One of my questions, I'll eventually put this up, is like, why is this a good construction to do? Is there any sort of physical explanation of why you should do this? But bear with me, let's do it. So if I take the fixed points of this finite subgroup in N, well, that contains an action of finite subgroup of mu n in the loop group. So remember, the flavor group normalizes G, so there's a well-defined action of mu n there. And if I look at the fixed points, there's a nice description of them. It's basically a scaled copy of my original loop space. Essentially, all I have to do is I have to make the loops n times bigger. So if I have some loop, this guy's, anyways, I can do this. And I just have to, unfortunately, I have to add in a factor of t to the minus phi. And here I have to conjugate by that guy.
You're trying to describe Bezrukhavnikov's construction in this language? Is that the...
Yes. So, right, my motivation for why to do this is if you sort of read this Bezrukhavnikov-Kaledin stuff and try to figure out what's happening on the Coulomb branch, it's telling you to look at these spaces.
And I have one more question. So in these papers by Tudor and others, do you have some variant of homological mirror symmetry for the category of line operators on the Higgs and the Coulomb branch? Is there some statement of that sort? Some
I
corresponding
believe
categories?
there's a conjecture of that sort.
By whom? By you?
By probably Tudor and those people. I mean, basically just saying, you know, if theories are 3D dual, the categories of line operators should be, you know, in the A and B twist should switch. I mean, right, that's essentially tautological, right? If it's the same theory, but you've just like changed your mind about which one is the A twist and which is the B twist, then of course the categories of line operators are going to switch. The question is just like, are there any actual examples where that happens, right?
Yeah, so what I meant is there's no statement, such statement of equivalence between the Higgs and the Coulomb branch of the same theory.
No.
Okay.
No, these are very different categories.
Okay.
No, the interesting thing that can happen is, you know, the same manifold can show up as a Coulomb branch of one theory and the Higgs branch of another theory. And at least in some of those cases, we hope that like the category of line operators in the A twist of one and the B twist in the other are equivalent. But no, for single theory, the A twist and B twist are
what you're trying to do now is give an explanation of Bezrukavnikov's construction, which sort of tries to construct coherent sheaves on some space via modules of quantization for that algebra in this framework, right, of symplectic duality. That's what you're trying to say, right? That it comes from the A twist to the B twist, right?
Let me get there. I'm trying to construct a window in this A twist, which will give me the same tilting generator that you get out of this Bezrukavnikov-Kaledin story. All right. Okay. So at the moment, I'm just doing some weird thing. I'm telling you, you should look at this finite subgroup of the flavor times the loop, and you should look at its fixed points. And its fixed points, there's sort of a self-similarity here. The fixed points look like, you know, essentially the things we were working with before. And actually, the interesting thing is, well, what happens if you look at the fixed points acting on the trivial line? So here we were able to just kind of conjugate away this story. But when you do this on the trivial line, you get something a little bit more interesting. So first, to think about this, you should think of the fixed points of this mu n on the affine Grassmannian. So this is the affine Grassmannian written in my notation. Well, it's going to be a finite union of orbits for this loop group where the loop is n times bigger. Is it n times bigger or n times smaller? Anyways. And I can describe those as orbits of, I look at the co-characters into my T, I look at the Weil group acting there, and then I look at translations that are scaled by n. So if I didn't do this scaling by n, this would be the affine Weil group. But I am doing the scaling by n, so I'm going to get a few different orbits. And so, for example, let's say in GLN, right, these orbits are, you know, fixed residues mod n, fixed unordered residues mod n. Unordered residues mod n. All right, and when I take one of these orbits and I look at how this scaled loop group acts on it, well, I get this guy, and it's mod some reasonable subgroup, but it's not mod G of O, it's mod a potentially bigger parahoric, which I can write this way. So I take G of O, I conjugate it, I have to conjugate it to account for the point where I'm acting, and then I intersect it with the scaled loop group. And that gives me, generically, it's going to give me an Iwahori. So in this example, if I take all residues different, All right, and over each component, so over for one of these orbits of the scaled guy, I get some component of the fixed points here. This is the guy corresponding to the trivial line. And they're going to be of this form. I take my scaled loop group, I take the corresponding parahoric, and I do a similar construction with my, I should put an extra pair of parentheses there, with my matter. I look at Taylor series in the matter. I have to act on that by some co-character, and then I intersect with this guy. So I get something that looks a lot like this trivial line, but it's a little bit different. It's essentially a line operator where instead of having the trivial line, I have some reduction to a parabolic along the line, and then I use that to say on this part of the representation, I have to have some zeros. On this part of the representation, I'm allowed to have some poles, and that exactly depends on what this lambda here is.
I'm sorry. So when you say the components are of these forms, what's the labeling? What's the index set for the components? Is the same?
The orbits of this group on the set of co-characters.
So the same kinds of index set.
Sorry. Yes, it's right. Every fixed point component in this guy is going to sit above a fixed point component in the affine Grassmannian. And it's basically just like you look at a point in that fixed point component and, oh, well, it's fixed under the finite subgroup. So the finite subgroup acts on the fiber over that guy, and you look at the fixed points of that. And that's exactly this guy.
Okay, so it's like the TZ quotient by NTZ give you some size N torus, and you fold that torus by W to get some weird shaped.
Yeah, I mean, the way I like to think about this, let me go to the picture a little further on, is, if you were looking at GLN, right, you can think of Z mod NZ as the N torsion points in S1. And that way you can kind of think of all N together. And each orbit is like putting points on the different N torsion points, right? Because mod N, you're not going to change where the points sit, and when you permute them, well, you're just changing which point is named which. And so free orbits correspond to when they're all distinct, and then if some of them sit on top of each other, I'll get some. And what that turns into in the affine Grassmannian is if they're all distinct, I get an Iwahori. If some of them coincide, I start getting a bigger parahoric.
Okay, cool. Thanks.
And from perspective of Tudor and physicists who originally studied this category of line operators, how would you explain to them that you have to do the Bezrukovnikov stuff, what they introduced N in the first place? What's the motivation? Just to get a finite algebra or what?
So what I would say is somehow like, I mean, at the risk of getting out over my skis, I would say that like, this is the real construction. I don't quite understand the details of it, but you have your 3D theory with some omega background, and you somehow look at the N torsion in the omega background, and that does something interesting to the line operators. I think that's the real construction. And all this characteristic P stuff was some way of accessing that when you didn't know about the field theory and you only knew about the underlying variety.
Okay, but why do we have to? Okay, good, fine. I'm happy with that. But why did we introduce N in the first place? What was wrong with the category of line? Sorry, maybe I'm not. I'm asking a very low-level question.
No. I completely understand. And I mean, again, maybe this introducing N, it's some. Maybe there's some better way of phrasing this, right? There is sort of, so it's maybe not extremely visible here, but if you let N get large, then what happens is, well, you get more and more components but more and more of them are the same line operator. So somehow, like, what you're doing, it really only depends on this var phi. Doesn't really depend on the n. There's some sort of stability as n gets large. And again, you know, that was sort of part of their story, that you do something for some very large prime. And so again, maybe there's some better way to describe this in the physics world. I don't claim that this is, you know, the right construction of it, but it's the one that sort of I understand most concretely at the moment.
Great, thank you.
Mm-hmm. So yeah, it's more that somehow choosing this phi and looking at the different lambda give me these subspaces. And so what's going to happen is when you let n get large, you're just going to keep getting the same subspace here many, many times. And so, you know, there are other ways you could describe those subspaces. This is the one that feels most natural to me at the moment, but maybe in a couple of years, I'll say, oh, that was silly. That was, you know, just some kind of slightly janky way of accessing what you really want to describe this other way, but I don't know the other way at the moment. All right, so looking at this fixed point component, we have a push forward to here. So we get a line operator, which I'm going to call S phi. And I can look at the endomorphisms of that line operator, again, in this sort of Chris Ginsburg way of taking a fiber product and looking at its Borel-Moore homology. And you might wonder why before I was always quotienting by this loop group, and now I'm not. Taking fixed points after you quotient by the loop group means something different. And I really want to take fixed points before I quotient. So that's why I haven't, where I'm including it in the equivariance here. But I get some algebra, which I'll call R, which is the endomorphisms of this interesting line operator. And so the theorem is, if your Coulomb branch is smooth, I should have put an L here, sorry, is smooth, oh no, I shouldn't have. No. If I take this Coulomb branch and it's smoothed out by looking at a generic mass parameter, then this guy, S phi, is a window. So you can think of this is actually big direct sum of objects. So you could take those objects separately, or you can take their whole sum. That defines a window for this resolution for any invertible vortex line. So in particular, the derived category of coherent sheaves on the partial resolution corresponding to that vertex line, which is an actual resolution because I assumed that MC was smooth at a generic mass parameter, is equivalent to the category of modules over this algebra. And so this guy R is what's called a non-commutative resolution of this. Oh, that shouldn't have an L, sorry. Of the original affine singular Coulomb branch.
And what's the nature of the equivalence? So let's say if we study the homes, are you saying that the homes between objects are simply, you know, the natural homes between objects in the derived category are simply equal on the nodes? Is that what the statement is?
So the way to think about this is that, as I said, you can take a coherent sheaf on this guy, and there's a canonical way to construct a line operator out of it, which you can think of as like this. You resolve by big negative powers of the ample line bundle, and then you turn those into line operators. And because I'm working with a vortex line, I can really say what that means. And then I take X of that with this line operator S, and that gives me a module or a complex of modules over this algebra.
And tell us again, what's special about S? What's this line operator S? So suppose I'm just studying coherent sheaves. What's S?
So S, I mean, what S is, I mean, it's telling you a particular coherent sheaf, right? So yeah, maybe a better way to think about this. I mean, I now that I'm thinking about it, maybe a better way to say it is, I mean, this S, this is a line operator, but I can thus construct a coherent sheaf T phi out of that. And I'm going to get that the self X of this coherent sheaf are R.
Oh, okay, sorry. So I think this is my usual confusion. Good, fine. So good. So T is just a tilting object, and
Yeah, exactly.
R is just okay. R is what you just wrote down. I see.
Yeah.
No, my question was rather different. Suppose I study. Well, I guess some people could be interested. Maybe I guess you were one of the people who were interested in the algebra, which is the original quantized Coulomb branch algebra.
Mm-hmm.
Okay. Do its modules. So I could study the category of its modules and derive category of its modules.
Mm-hmm.
Suppose I just want to do that. Okay.
Mm-hmm.
Is there any statement about relation of the derived category of the quantized modules for the quantized Coulomb branch algebra with this derived category in front of us?
So I think the answer to your question is that what's going on here is so the quantized Coulomb branch algebra, right, in characteristic P is the homology. We're going to have to go back to, I have to go back a really long way. It's the homology of this guy with coefficients in characteristic P.
Mm-hmm.
And well, if you want to think about the actual quantum guy, you have a C star that's acting, and you want the equivariant parameter for that C star to be invertible. And so there's some interesting connection of, oh, well, so in characteristic 0, if you invert the equivariant parameter for C star, then you might as well just pass to the fixed points, right? The equivariant cohomology with the equivariant parameter inverted is the same for the whole space and the fixed points of the C star action, assuming everything's equivariant.
Are we talking now about a very special C star action that scales the homomorphic symplectic form, or any one of the other C star actions that we have around?
Well, here I'm talking about the action on this BFN space. Right. So I'm looking at the homology of this BFN space. You know, I should say, like, right, if I want a star product here, then I should take C star equivariant homology.
Yep.
And so, you know, there's some interesting story about what happens when I actually pass to the full C star fixed points and the characteristic 0 representation theory of this guy. Now, if I take coefficients in characteristic P, then that theorem isn't true. It's not true that the fixed points of the full C star and the whole space have the same equivariant cohomology. But it's true if you look at the fixed points of the P torsion.
Mm-hmm.
And essentially this becomes like, you know, the original proof that the fixed points are the same involves inverting the Euler class of the normal bundle to the fixed points. And that's not invertible mod P anymore. But the normal class to the fixed points of the P torsion will be invertible. So I have never managed to like put together all the magic algebraic topology words to sort of say what's going on here, but somehow that should be the explanation of why doing this characteristic P story is related to looking at the fixed points of the P torsion in the loop action. But I really think you should thinking of those fixed points as a more basic thing, and the characteristic P story is some way of accessing it. I mean, I can't prove it, but that's my thinking at the moment.
Okay, I suppose I'm asking like this. For some representation theoretic purposes, people are interested. Well, sometimes these quantized Coulomb branch algebra is actually interesting algebras, and maybe someone wants to look. People like you want to tell us that these well, these are very natural generalizations of interesting algebra, so hence they are good things to study. And you might want to study, for example, Kasdan-Lustig polynomials and stuff like that for these quantized Coulomb branch algebras. Okay.
Yeah.
My question is, can you recover them from the derived category in front of us of R mod or coherent sheaves?
Yes, as long as you do some finiteness, right? So like if I looked at finite dimensional R modules, that would be the same as looking at coherent sheaves that are supported on like the fixed points of the core, the stuff that's
I see.
That has a limit under the scaling, and this would be equivalent to also finite dimensional modules over the quantization.
And what's the logic there? Why does this happen?
So I have a pretty explicit algebraic proof. And I think there should also be a topological proof along the lines of what I just said, that you have some localization that works when you pass fixed points under P torsion. Okay, great. Thank you. Thanks, Ben. Yeah. And I like to, for purposes of, if you like thinking about sort of, I get some resolution when I make the Kahler parameter generic, you should think of these as sort of the resolutions that come from having purely imaginary complexified Kahler parameter, and this complexified Kahler parameter telling you something like, what should phi over n be? Times I. Right, so, I have to say, I don't understand what the physical meaning of this construction is. I would be really happy if anyone could.
Can you explain why is that? Why it corresponds to the pure imaginary Kahler parameter?
Things work out when you think about it that way. So I don't have a really good explanation. But the main reason is it sort of makes the story about, to do with it is sort of one-dimensional family, like along the complex imaginary line or something like that. It makes this sort of picture of thinking about like functors coming from varying the complexified Kahler parameter work out well. So that's sort of my reasoning.
Mirror symmetry, two-dimensional mirror symmetry makes this manifest. It completely explains this fact. So,
all right, great. Good. Yeah, I really like. You should tell me at what point I should stop.
We let our speakers tell their story. So have no fear that we want you to tell our story. That's why you're here. So,
okay. Well, have no fear. But I think this is all sort of stuff you've already pulled out of me. That I think this characteristic P story is actually just a way of trying to access this when you don't know about the field theory. Don't know about omega background. All right. So one of the reasons that I mentioned at the start that we would be interested in these windows is we get equivalences between coherent sheaves for different resolutions. You get different equivalences for different phi. So when you combine these all, you get an action of T pi 1 of take the flavor torus itself and then pull out all the points that sort of are non-generic complexified Kahler parameters, right? You can think of the complexified Kahler parameters living in TF. And so I'm pulling out the non-generic ones. And maybe to answer at least a little bit Peter's question, right? Somehow the way I think about this is you have this torus, so like you have a unit circle, I mean, I'm drawing a one-dimensional example. And then you'll sort of have two ways of going off to infinity. You'll have going to zero. In this case, you'll going to zero and going to infinity. In higher dimensional examples, you'll sort of have different things in different directions. And these guys correspond to the different commutative resolutions, because I'm sort of, taking some big power of a line bundle. Sorry. And so my equivalences I should think of as like a path going from very far out one direction to very far out another direction. But I get different ones if I go through kind of different chambers on here. There are some bad points on here that don't correspond to resolutions. And if I sort of go, through one gap going one way using one choice of phi and go through another gap the other way using another choice of phi, I'll get some interesting auto equivalence of this derived category of coherent sheaves. And these are exactly these. Yeah.
The story that you told us, does this hold in generality of Leisner's work? In other words, when the Coulomb branch is a GIT quotient itself, or is it more general than that?
So I would say it's actually less general. So there's one sort of tricky point, which is I wanted you to have smooth Coulomb branch at generic mass parameter. And that's actually a pretty restrictive assumption. Probably we don't actually need that. Probably there is some weaker version of this, but some of the proofs I sort of haven't tried to make go through it if you don't have this assumption. So the smooth at a generic mass parameter, like the only examples I know are the finite type ADE quiver representations, affine type A quiver representations, and toric things.
Right, but as far as Coulomb branches go, that's less, right? Because you're just going to get the toric and Coulomb branches of either toric gauge theories or type A gauge theories, right? Because
Or
otherwise,
type A.
yeah, great, okay.
Or type D or type E. Yeah, so it's not that general, but probably it actually works in other cases. Probably you don't need this this restriction.
No,
but
sorry, in type D and E, Coulomb branch is not a quiver variety.
That is true. The theorem still holds.
It still holds. I see. So
Yes.
so then it's broader than hyper because you don't have a GIT quotient. Coulomb branch is not saying it's an Nakajima quiver variety or a GIT quotient, or that it's a it's a Higgs branch of a gauge theory. We know it's all the same thing, right?
You can see it. You can construct it as a GIT quotient of something like really horrible. So you can do this story of add in the flavor torus to the gauge group, look at the Coulomb branch for that, and your GIT quotient of that guy. Okay. And that's there's an element of like any projective variety can be written as a GIT quotient, right? Okay. Because you look at its affine cone and look at the C star action on that and do the GIT quotient for that action. So somehow able to write it as a GIT quotient is a vacuous requirement for a projective variety. Yeah, so it's more, what's interesting is actually having some control over what these bad points are, knowing that they're like exactly the guys that correspond to bad complexified Kahler parameters. All right. So, that's most of what I wanted to say in the general story. Obviously, I could try to make more general statements about this action. But the other thing I wanted to say, which maybe I'll just go through rather quickly because it's getting late, is I wanted to talk about how this actually applies in the quiver gauge theory case. So consider a quiver gauge theory coming from, I drew the nice picture here. I have some nodes, circles with V's in them, squares with W's in them. and consider the corresponding quiver gauge theory. As I say, the theorem that I mentioned before can only be gotten if we have smooth Coulomb branch here. So if either gamma is type ADE, and there's also affine type A, but you have to do things a little differently from what I'm going to say to get affine type A. In this case, these spaces, this loop space and this arc space of n mod G, you can think of as quiver representations over Laurent polynomials or quiver representations over Taylor polynomials. So they sort of have a nice moduli interpretation, and this BFN space is quiver representations over Laurent polynomials with a choice of two lattices that are invariant under all the quiver maps. If I choose a co-character into this GL of CW, and this is where I would have to do something differently in affine type A, I would need to also incorporate some extra flavor that comes from the cycle. But this is sort of simpler. Going into here, well, what's a co-character into a product of GLNs? It's I have to decide what weights I want my basis vectors to have. And so I end up with an n tuple for each GLN. So I have an unordered tuple of weights. And as we were discussing earlier, I think of those as points on a circle where I embed Z mod n as the n torsion points on the circle.
Why do you single out affine type A? Why can't you do a affine D and E as well?
Because if you look on the Nakajima quiver variety side, there isn't a C star action with isolated fixed points. So what's special about affine type A is you get an extra flavor parameter coming from the homology of the cycle.
I see, but also the D-type quiver that you wrote down would also not have isolated fixed points, right? Because these four representations that you chose were not minuscule.
Sure.
Right.
Yeah, sorry, this was just to kind of represent.
Yeah, okay. So it means it's the minuscule condition. Okay, fine. Notice, I suppose, yeah, okay.
Yeah, I mean, somehow like, yeah, if you look at affine type D, there isn't some extra flavor parameter that you get like you do in affine type A. So, that's just how it goes. So now I look at my fixed points for this mod P action. Remember, the reason I'm thinking about this on the circle is I'm only looking at fixed points of the n torsion inside my S1 or my C star. And so as we discuss, the components of these come from, for each VI, looking at an unordered VI tuple of residues mod n. And so I can also represent those by putting them on the circle. And I need to remember which node in the quiver they correspond to. So this number written next to them, that's the corresponding node in the quiver. So a picture like this corresponds to one of the components of my fixed points for this Z mod n action. And I had made this comment about, well, when n gets large, things sort of stabilize. So the corresponding line operator only depends on the ordering of these guys on the circle. So if I sort of move these guys around on the circle without crossing anything, then actually I get the same line operator.
Sorry, Ben. Can you say again what's the numbering on this? On the red dots means?
So this is, remember, I need to choose a co-character into GLN CVI.
That's right.
So and then I'm going to look at that up to conjugation and sort of scaling things by t to the n, right? So that co-character, I end up with a bunch of integers, and I want to think of them as an unordered VI tuple. And I'm only considering things mod n, but I have a different one of those for each node of the quiver. So like the ones numbered 1, you know, I have one thing numbered 1. So like
maybe I'm asking a question,
one,
similar question. This is just the first picture, not the black and
oh, I'm
red
sorry.
picture.
With the first picture,
Yeah.
well, again, these numbers, that's which of the GLCWIs I came from.
So the thing labeled by 1 are things for W1.
Yeah, for the node
First the box.
Yeah.
Uh-huh.
So like these.
I see.
Correspond
Okay.
to actions.
And what are the locations? How are the
locations are
the CI?
what is the actual weight that I'm acting by?
I see.
So I'm acting on quiver representations.
So you choose, you have to make some generic choice so that they have distinct model points. And these black dots, these are also just generic choice.
Well,
No, these are fixed points. Yeah.
I'm going to have different components of the fixed points of my Z mod NZ.
Yes.
And the different components are going to correspond to different ways of positioning the black points.
Okay, so those are
Each way of putting the black points on the circle gives me a line operator, and I'm going to take the sum of those over all ways of putting those on the circle.
You should also visualize them using Young diagrams, right? So like for every framing node, there's like a fixed point which you can associate the Young diagram, right? And then because you can, those numbers will be like the something like height number in the Young diagram if you put it in the 45-degree angle, something like that.
Okay.
There's some combinatorial.
It's more complicated than that. There is an interesting connection there. But it's a little more complicated than that, in part because the story you just said, that involves this C star action on the cycle.
Yeah, I know. So there's an equivalent parameter that comes from the loop, right? So, which is
so it's, anyways, I could explain what you need to do to bring that into the picture, but it's not here at the moment.
Ben, so just a question. The configurations of the black dots are in one-to-one correspondence with the fixed points on the Coulomb branch, right?
No, they're giving me, so.
Or is there more?
There are many more, right? I mean, there's this issue about like, oh, as I let n gets big, there are sort of lots of different places I could put the dots that all have the same order. And so I get a lot of redundancy. I get a lot of dependence on it.
Up to equivalence.
Oh, so, maybe, I'm sorry. I think I misunderstood your question. So yes, a component of the fixed points for the Z mod NZ action corresponds to the ways of putting the black points on the circle. Yes. Sorry, I was thinking, but it's not on the Coulomb branch itself. It's on the BFN space. So fixed points of the Coulomb branch is some very, very different story.
True or false? If you just keep track of the ordering, and so if we just ask about different orderings of the red and black dots, then we have one-to-one correspondence between the orderings and fixed points on the Coulomb branch.
I don't think so.
You still don't. But the orderings corresponding to, there is still some correspondence between fixed points and the orderings. Those orderings play a special role for you, don't they?
I mean, I think you might sort of have some version of what Peter was trying to come up with, that like for fixed points, there's some special, for each fixed point, there's some special way of arranging it that comes from the corresponding Young diagram.
No, forget it. So Young diagrams are going to be for the affine type A. Let's not worry about affine type A. We can just talk about representation theory. The number of fixed points on a Coulomb branch. Okay, so let's talk about, just suppose we're in, AD type, not affine AD, just AD type.
Yeah.
Then the fixed points are in one-to-one correspondence with the weights in some representation, right? That's attached to the Coulomb branch quiver. So it has some representation theoretic meaning. If they're isolated. In fact, no, even if they're not isolated, they're always in one-to-one. Isolated. Okay. Right?
Yeah, so I mean, it's there. I think it may be true that like simple modules over the algebra correspond to fixed points. I think it might be possible to make that work, but that's, I mean, you know, kind of has to be like the size of the K theory. It's
exactly.
it matches up. But there's a lot of redundancy here. There are many more of these guys than there are simple modules. And there will, you know, there's some very complicated like thing of, you know, which, you know, each one of these guys gives you an idempotent, and there's some complicated correspondence of which simple modules does the idempotent act non-trivially. There will be multiple different idempotents that act non-trivially on the same simple module. There will be idempotents that act non-trivially on multiple simple modules. So yeah, there is some connection to the fixed points, but it's more complicated than that.
Okay, but every ordering gives you a line operator?
Every ordering gives you a line operator, yeah.
And a coherence sheaf.
Yes, and a coherence sheaf.
Okay, great.
And you know, another way to say what I was going to say is like that coherent sheaf won't be indecomposable. It can break up as a sum of different smaller coherent sheaves, but in some way that's very hard to predict.
Okay, great.
All right, so these give me components of that fixed point set, and homology classes in the fiber product can be represented by diagrams drawn on this cylinder. So this algebra, I mean, this is also this algebra I was calling R, its elements can be drawn as these sorts of diagrams, mod certain local relations, these being the kind of most obvious ones. And they're
Okay,
essentially,
just one more question. You allow then all possible orderings?
I allow
any
all
ordering goes,
possible
right?
orderings, yes.
Yeah, okay.
Yeah. Right, and then, you know, you have to prove some theorem of like, oh, well, actually, every simple module has one of these orderings that actually comes from a Young diagram, or, you know, more generally, one of these weights that has a non-zero product with it. Yeah, so there's, I mean, there's some version of that story, which, I mean, honestly, I haven't really developed. I probably should, but, you know, I got other things I need to do with my time. All right. So it's, you know, I just want to emphasize it's an algebra we can really get our hands on. It's sort of these concrete cylindrical diagrams, modulo some local relations that these are two examples of, and they're, if you know about Kahler algebras, they're the relations coming from Kahler algebras. And wall crossing functors you can also describe in this world by, so my red lines, the other way to think about the position of the red lines is it's telling you this complexified Kahler parameter that is purely imaginary. And so drawing a picture like this where the red lines move, that's a path in the space of Kahler parameters. And so there's a bimodule corresponding to this line that gives me the wall crossing.
Do you mean like there's some undercrossing, overcrossing for the red line? You pick some convention?
So in terms of the bimodules, there's no choice of under versus overcrossing. But yes, for the path in the space of Kahler parameters, you have to make some choice of how you go around that singular point.
So how do you explain the fact that your bimodule corresponds to one way of going around and not the other?
Because you can tensor with a bimodule, or you could hom with the bimodule. And tensoring with the bimodule corresponds to one way of going around, and hom with the bimodule corresponds to the other way of going around. And it's kind of arbitrary how you match the two up. So, right, like if you have a bimodule such that tensor product with it gives you a derived equivalence, then the inverse to that derived equivalence is taking hom with the same bimodule. So it sort of has to be, if one of them corresponds to an overcrossing, the other one corresponds to an undercrossing. And yeah, it's easy to get confused about how everything matches up, but you know, at some point it comes down to, you know, some choice about like when you took that pre-image, did you choose the left adjoint or the right adjoint?
Do you have some good description of these bimodules? Say, Kovanov and Seidel, they have some like, nice projective resolutions of the bimodules. Do you have anything like that for these?
Basically only for SL2. For SL2, there's sort of a reasonable description of these that, basically it's basically this Barnaton story that, Barnaton tells you how to kind of resolve a crossing in terms of diagrams with no crossings, and a similar kind of resolution exists here.
But you should be able to derive all this from coherent sheaf story if you understand it really well, right?
Yes, but I think it's easier to do the diagrammatic stuff and then translate that into coherent sheaves than to try to do it the other way around. And in the higher SLN cases, you can try to use this foam picture. I don't know if that actually is really simplifying things, but it's providing you a kind of resolution. And one of these things.
Oh, one would like to do things from geometry, right? So
depends on your perspective, right? There are certain things that are actually very hard to see in geometry, and which are not too bad if you think about these algebras. So that's kind of why I like them.
Well, can you do calculations with these diagrams?
I mean, again, mainly in SL2. So no, I mean they're not the best adapted to doing calculations.
So for example, one can describe explicitly, the action of ray group on the tilting generators. I essentially know how to write it down in full generality, but the question is, to connect it to your picture, to understand the resolutions of bimodules. Those things I don't have the algebraic muscle for, but they're certainly doable from geometry, but then one needs to do the algebra.
Yeah. Well, yeah. So there are certain things which are good about this picture. There's certain things which are bad about it. I mean, my justification for connecting it to the non-homology stuff is it lets you compare with the earlier non-homology work.
How sure are you that this gives the Kovanov homology?
I mean, 100%.
100%?
I mean, right, like somehow I would say it's like more likely that there's some subtle mistake and the whole thing is wrong than the general construction is right and it's not Kovanov homology.
Well, Kovanov homology has over Z2, over like there are lots of stuff you can write down.
Okay. So yeah, over the rational numbers. I would need to think harder to think about the like Z part.
Okay, I see. Yeah.
So yeah, I am less sure about over Z, but yeah, I should think about whether I'm convinced that that's correct. I mean, it should still be over Z, but maybe some, I could imagine some subtle thing happening with the signs, basically, right? They're sort of, I mean, basically you're what's happening is you're getting an action of this Barnaton category, essentially. I mean, a cylindrical version of it, actually, but I could imagine some signs snuck in some.
No, I think that some differentials could be missing.
Yeah. Oh, differentials missing?
Yeah. I think it's quite possible they're missing. So once you do the SL2 story, I think if it's not exactly the same, it's actually a good thing.
Yeah. I mean, so from this perspective, I don't think there's any way
sorry, I apologize. Go ahead.
From this perspective, I don't think there's any way there could be differentials missing. Somehow the differential is built into the structure of this bimodule. The differential that comes from the fact that if you open this crossing, you get a map into the identity bimodule, but it's not an isomorphism because you can't get, so you have sort of this picture, you split it open here, but you can't get this guy. So all the diagrams that have a black strand going between these two reds, that's the co-kernel.
Yeah, no, I think I understand your resolution
corresponds to-
geometrically. I think that that resolution makes sense. I'm just not 100% sure. So firstly, in physics, the natural thing to do is like calculate over C, not, yeah. But anyway, go ahead.
Yeah.
Yeah.
Okay. Well, that was basically about done. I was just going to say you can extend this to non-homology by adding in cups and caps. And I mean, this is stuff from talks that Mina has already seen. When you combine all of these together, you get a functor from oriented affine ribbon tangles labeled with minuscule fundamentals. So to each sort of to each way of putting things on the top or the bottom, you have this algebra R. And so this, you know, when I say there's a functor to DG categories, you know, what I mean is I can take this picture with the red strand sitting here, and that goes to, you know, the derived category of R modules, maybe finite dimensional if you want. And then every affine tangle joining those gets sent to a functor between these categories. And using this, you can compare Mina's work with my older non-homology work, and in particular compare that with Monoverzonsky in type A. But since Mina brought it up, I should say this is over like C. So yeah, I have not thought extremely carefully about Monoverzonsky and over Z. All right, and I'll just skip that part. That's not that interesting. So thanks everybody for your patience.
Thank you, Ben. So how explicitly can you connect this your braiding by modules to the geometric ones? Or the action of braiding?
So by the geometric ones, you mean?
Well, you just told us about these wall crossing functors, right?
Yeah. So I mean, it's very explicit, right? It's because it's really like another way to answer your question about like how do you know which one is overcrossing and which one is undercrossing is to compute the wall crossing functors. You know, essentially what you have to do is you have to take two tilting bundles and compute R-HOM from one to the other.
Yeah.
Right. And you get that bimodule, and then like tensor with that and HOM with that give you like two different equivalences between the non-commutative resolutions. And so, you know, it's just a matter of if you set things up right, R-HOM between the two tilting bundles will be just like computing X of the tilting bundle with itself, and it'll just be this set of diagrams.
With a braided tilting bundle, or the tilting.
Yeah, I mean, if it's two different tilting bundles for two different things. So it's sort of, I mean, it's relatively automatic. Like where this comes from, this, you do things over, so you can interpret this guy as endomorphisms of a line operator for the theory where you add in the flavor torus to the gauge, and like you do some computations with that theory, and so it ends up being relatively automatic.
Sorry, I didn't understand this.
So this moving red lines around, you can think of that as like a co-character in the flavor torus. And so you can think about the theory where you expand your gauge group by also adding in the torus of the flavor group. So now you have a bunch more like monopole operators. operators. And these pictures where the red lines cross, they exactly correspond to like monopole operators that use some non-trivial co-character along that.
Oh, but that doesn't help with computations. In the end, you need two tilting bundles, and you need to compute the Helms between them.
Yeah, but the point is, you know, those two tilting bundles come from doing
Yes,
a
they come from
DIT
that.
quotient from, yeah, I mean, it's been, I would want to like look at the paper to remind myself like what you actually have to do, but my recollection is it's actually pretty, pretty abstract. Like you just sort of, like the reason it could be this guy is essentially not computation, you know, using the
Yeah,
bigger picture.
right.
And then you just have to do a little bit of work to show like, well, why is it this thing you would expect it is?
Yeah, I'm just bothered a bit by sort of asymmetry. You have to come up with some arbitrary rule about going forward versus going backward. I don't know. You know, grading one way versus the other way. That's a little unnatural. On the other hand, maybe this is some fact of life.
Well, you know, it's something about where you have to choose what resolution you're looking at the tilting bundles on. And so that choice of resolution gives you some preferred direction, right? Like it tells you which one you should make the overcrossing and which one.
No, I mean, you can certainly, you know, get, one can get the full action of braided group in one way or the other. The question is how to translate, I mean, a priori, right? You get a home to the positive rating and a home to the negative rating. And you have to somehow decide that you're going to assign them to this picture in two different ways.
Yeah, I guess what I mean, so there is this element of like, I remember being confused about this point, and I kind of remember at least coming to peace with it, but I don't remember as clearly as I should exactly how I did. So, you know, I agree that it's easy to get kind of mixed up about like, why does this thing go to this thing?
And actually those kinds of complexes you were writing down in Kavanaugh case, do you have such a thing in general for arbitrarily algebras? Do you know?
Yeah, I mean, in the sense that, so, you know, these pictures that I'm drawing here, you can interpret as paths in the torus of the extension of gauge by flavor. And so I can sort of tell you a general rule for like, you know, think about certain kind of paths in that torus and apply like local relations to what happens when those hit certain subtori.
I mean, in the end, it's just a pictorial depiction of certain homes, right? That's
yeah.
all you're doing. And then the question is, okay, so which home should I be doing?
Yeah, but you know, like, right, so you can think about, you know, monopole operators correspond to co-characters into the gauge group. So you can think of that as like, you know, a path in the actual torus of the gauge group. And there is a like rule for the multiplication of like monopole operators, which is like, you know, compose those two paths and then do some local rule for kind of straightening things.
Yep.
And, you know, somehow like these pictures are translating that general thing into, oh, well, if I'm in the case of my gauge group is a bunch of copies of UN, then an element of the torus is a bunch of points on the unit circle, and a path in there is a picture where those move around on the unit circle. And then like the sort of local rule for moving the path around turns into these kind of local relations, right? So this kind of bygone, that's like a path hitting a hyperplane, going through and then coming back across the hyperplane. And there's some general rule for what happens when you do that.
Yep.
All right, thanks everybody for sticking with us. I guess it's much earlier there for you. I'm ready to go to bed.
Thanks for coming and telling us a story.
Yeah, of course. And you know, I'm happy to address any questions any other time if people think of them later.
Great.
Thank you, Ben. See you, everyone.
Yeah.
Thank you. Thank you, Ben.
Thank you.
Thank you.